I'm so bad at calculus. I wish there was some way that I could know how the people that discovered it knew how to do it. Miss Lasnier, is there any other way that I can learn calculus?
Well, there is this one thing I haven't told anyone about. Are you interested?
If it can help me out, yes.
Okay. You haven't eaten recently, have you?
No.
Okay. Here we go.
Whoa, where am I?
It's not where you are, brother, it's when you are.
What? Who are you? What does that even mean?
My name is Archimedes of Syracuse, and I'm the first person Leanne Lasnier sent you to teach you what you know as early calculus. However, today it's called exhaustion and analysis. And by today, I mean the classical age of 230 BCE.
What? So you're telling me I'm 2,500 years back and talking to the Archimedes?
Why, yes.
And I'm not the only person to have come back in time?
Why, yes. Leanne Lasnier has perfected the forgotten magic of undefined physical bodies and has used the art of dividing you by zero to send you back in time. She heard your wish of discovering more about the history of calculus and has literally made it possible. I am responsible for setting up those later on to discover calculus and its modern definitions. More specifically, the method of exhaustion. First, I took a curve and then drew a shape under the curve. Finding the area of the shape, I was able to find an estimated area under the curve. I then realized if I drew more shapes, I could more accurately predict the area that was under the curve. Finally realizing if I used an infinite amount of shapes, I could find the exact area underneath any curve I drew, thus exhausting all possible areas under the curve.
No way, Archimedes. I learned that.
I know. I was also able to use exhaustion to derive a number for pi. I realized that the ratio of circumference divided by diameter was central to many formulas in finding the area and volume of other shapes. To use exhaustion, I first drew a circle, drawing hexagonal shapes in the middle, with each corner touching the edge. Then I drew the same shape on the outside. And using the diameter and circumference of these shapes, I was able to approximate a number for pi. Then, adding infinitely more sides to these hexagonal shapes, I was able to exhaust the exact number for pi, 3.1415.
Yeah, dude, I get the gist. But wow, thank you so much for teaching me so much and opening my eyes about just how you discovered calculus. Now can I go home?
Well, good son, that is up to your philosopher, Leanne. Except, if I remember right, I think you have a little bit more to learn.
Welcome to your second stop on the journey through calculus. I'm Hassan Ibn Al-Fahim and I have so much to teach you.
Epic, let's get to it.
So you're not going to ask who I am?
No, at this point I'm kind of just rolling with it, honestly.
Okay, anyways, I'm one of the most famous Arabic mathematicians because of my work in calculating the volume of the paraboloid. A parabola rotated on an axis.
How'd you ever manage to do that?
Well, I actually used the help of the discoveries of Archimedes and saw that the volume could be calculated by finding the area under the curve of the line of the axis. At this point, you would be able to plug in these values to any number of formulas, but I lived 700 years before these were even thought of. Instead, I found the approximate area by stacking discs together of certain radii and exhausting the volume of the parabola.
Whoa, that's the exact same way Archimedes did.
Almost, not quite. I was then able to isolate these values as an equation.
That's crazy, dude. Good for you. It's really as simple as that, I guess.
No, not at all. This took many other scholars and years to discover.
Well, thanks for speeding it up for me. Where am I going next?
If you ever care about, is it?
Oh, great. New places.
Welcome to Demont de la Malfra. I am the greatest mathematician, Pierre de Fermat. I assume you are here for my infinite knowledge on calculus.
Totally, dude. Lay it on me.
So it all started when I discovered a theorem on minimum and maximum values of lines. It is the backbone of most minima and maximum physics and is called Fermat's stationary point theorem.
Sounds official.
This is where, if the graph is differentiable on the interval a to b, and there's a maximum and minimum point c on the curve, then the value f prime of c is equal to 0, or the slope at that maximum or minimum point is 0. Thus, I have found that any relative maximum or minimum point on a differential graph will be 0. It is sounding like a function of calculus.
Oh, epic. We use maximum and minimum slopes in so many things back in the future.
Back in the future, that would make a great French play.
No, you'd actually be copying the movie.
What?
What?
What? Anyways, you should be going soon. But don't forget to tell your friends I also invented modern number theory and analytical geometry. Bye!
Gosh, I hope I meet Einstein this time.
Fortunately not. You get to meet the inventor of modern calculus, Isaac Newton.
Well, that's second best, I guess. What type of knowledge are you going to throw down for me right now?
Well, it all started in the year 1685, when my university, Cambridge, closed due to a plague outbreak. During this time, I was able to create a form of differential calculus called fluxions at age 22, one more than 21.
Wow, that's the same age as Lil Pump, Small World.
Little pump? I don't think those are invented yet.
You're right, but in 2 years a Frenchman will do this.
I'm sure an Englishman would have invented it better. Gucci gang.
Good to see some things never change. Anyways, tell me about fluxions.
Well, these principles were how I discovered my famous 3 laws. Drawing upon the work of Fermat, I figured out how to find the slope of the tangent line of any point on a parabola. This is called the derivative. After this, he saw that finding the area under the curve, he being me, the integral, was the reverse of finding the derivative.
Wait, isn't that the fundamental theorem of calculus?
Quite right, my friend. I used a momentary rate of change to find the change in area under the curve. Based on Archimedes' findings on exhaustion, I reasoned that infinitesimally decreasing the change in x value, later coined dx, would produce a new formula, x equals x plus o, where o is the change in x.
That's sick. But why fluxions in x values instead of calculus and dy dx notations?
We do not talk about the man who made those. Leave me! You have been divided by 0.
I wonder what that means. Now I kind of want to meet this guy.
What guy?
I'm thinking you, guy. What's your name?
I am Gottfried von Leibniz, the true inventor of calculus. You must have come from my counterpart, Sir Isaac Newton.
I sure did. But why do you guys beef so bad?
Well, it all started in the late 17th century when I started publishing my amazing findings on early modern calculus. I was able to create and popularize the math terms dy dx, ever heard of it? And the term calculus instead of the previous term fluxions. I even invented the modern equal sign. Who else could say that besides me?
Wow, that's great, but I see no problem with you and Newton at all.
Well, that's where it starts to get interesting. At the same time as I really discovered calculus, Newton claimed that his findings were over 8 years old, and therefore he really invented calculus. That means that he took my ideas on area under a curve, instantaneous rate of change, and delta x.
Wow, he just decided to publish his findings conveniently at the same time as you, even though there were 8 years of lead up?
Real believable, right?
Yeah, looks like I'm Team Leibniz.
That's great to hear. Now, when you go on, remember, I may not have done it first, but I did it the best. Leibniz out.
Hello, Brün. Welcome to Germany in the 19th century. I am Karl Friedrich Gauss.
Guten Tag to you too, Mr. Gauss. What kind of stuff did you create?
Well, I, among many things, created binomial theory that allows one to expand upon polynomial. First, you start with your polynomial here, raised to the nth power, and that is equal to the sigma notation that expands into the polynomial here to the nth degree in k signifying 0.
Wow, that's a mouthful. But I always remember using binomials since middle school.
Well, that's not all. I also created fundamental laws of electrophysics called Gauss's law that allows you to calculate the electric flux in an object. First, you find the charge enclosed by taking the integral of the...
Wait. I thought this was a math.
Oh, you're right. Anyways, some famous examples of binomial theorem are x plus y to the second power is equal to x to the second power plus xy plus x plus y to the second power, and x plus y to the third power equaling x to the third plus 3xy to the third plus 3x to the third y plus y to the third.
Where am I now?
Another one. Does Lasnier have that much trouble teaching your students? Bonjour. You would call me L'Hôpital. Welcome to 17th century France, the land of math and croissants. Speaking of which you want one?
El Hospital? I think I hit my head too hard. Did I time travel to the emergency room?
Not quite, my friend. But I do have a rule to teach you that may make your head spin. I call it the super cool top-down differentiation rule.
That doesn't quite roll off the tongue. How about L'Hôpital's rule?
Not the creative one, Arby, but I like it. From now on, my rule is called L'Hôpital's rule.
Well, let's hear it.
Yo, listen up. I got a math lesson drop. L'Hôpital's rule to make your limits pop. When the limits approaching 0 or infinity, this rule subtends to solve the mystery. L'Hôpital's rule, let me break it down. Use on a fractions to talk of the town. Take the derivative of the top and bottom. Repeat if needed, simplify no problem. Indeterminate form, impossible to solve. With L'Hôpital's help, your brain will evolve. Just apply this rule and you'll find the solution. Derivatives to help with this mathematical fusion.
Wow, thanks so much for teaching me L'Hôpital's rule in such a fun way. Now I totally get it. But can I finally go home now?
Of course, I'll show you my secret form. I call it the croissant rule.
Wow, Miss Lasnier, it sure is good to be back. I learned so much from all those super smart old people from the history books. Newton was my favorite, though.
Oh, that's really good to hear, Boone. And remember, by paying attention and learning calculus, you could be the next stop in the time travel history of calculus.